Yeah, it's okay. Yeah, do you have a pointer?
You have a pointer here. So hold it for just a second, so that it will get activated.
Okay.
Like
Okay, fine. Okay, so first I would like to thank the organizing committee for this great meeting. So over the next 12 minutes, I will try to show what we might be able to do in the near infrared with the Roman, thinking about transients behind large amounts of dust. So of course, I mean, these days we have a number of wide field optical surveys discovering optical transients really at accelerating rates. But I think the near infrared side has been a little bit neglected, and I think Roman can actually open very good opportunities there. So we put in this white paper 1 year ago. So I list my collaborators here in the white paper. So this was actually for the high latitude wide area survey. So it was one of the very few white papers proposing to use the wide area survey for transients. So if there is a possibility to actually split the observations into even 2 epochs or more epochs, we will get many transients. So I will show some examples here concentrating on the dust obscured events. So I will be talking about these lurks and U-lurks, luminous and ultra-luminous infrared galaxies where we have huge amounts of dust. So these are very rare events in the local universe, but then when moving further in the redshift, we see that they actually start dominating the co-moving star formation rate density when we move to a redshift of 1 and above. So then considering the transients in these kind of galaxies, they actually might be very important at higher redshift. But then, of course, when studying the transient populations, we are limited to the local examples of such galaxies. I'm showing one nearby example here. So this ARP 299, a famous example at about 50 megaparsec distance. There is an HST optical image here, and then we zoom in to the nuclear regions using near infrared with the HST and Gemini North with adaptive optics. And here we actually see that one of the nuclei of the galaxy has brightened by a big amount over 10 years' time. So I will talk more about this transient actually in the next slides. So the very high star formation rates mean that we also expect to have extremely high rates of core collapse supernovae when these massive stars live their short lives and then die at the end as core collapse supernovae. So this means that we might actually expect core collapse supernova rates which are orders of magnitude higher than any normal field galaxy. So we might get 1 supernova every year. We might even get 10 supernovae every year in these more luminous examples, luminous and maybe ultra-luminous infrared galaxies. These are not visible by optical surveys because of the high extinction, so we have to move to the infrared or radio to have any chance of detecting these. There has been a number of efforts in the infrared, so I just listed a few examples here, but there are actually many more examples. So why we are interested in transients in supernovae, in luminous and ultra-luminous infrared galaxies? Well, one possibility is using core collapse supernovae as probes of the cosmic star formation history. So there has been a number of efforts on this. I think JWST will open new opportunities there as well. But then, as we know, we have an increasing fraction of star formation happening in lurks and U-lurks when we move on in the redshift. So we expect to actually have more severe effects by the dust extinction for the supernovae. So we want to know how many supernovae we are actually missing in luminous and ultra-luminous infrared galaxies, even locally, and then we might try to work out how many we are actually missing as a function of redshift. So that's one science motivation. There are many more. So then moving on to a slightly different type of transient, tidal disruption events by supermassive black holes. So again, in luminous and ultra-luminous infrared galaxies, we often have an active galactic nucleus, so we have supermassive black holes there in the center. We have often interacting galaxy mergers, so we might expect enhanced rates of this kind of tidal disruption events by the supermassive black holes in these galaxies. So we expect bright flares of light in X-rays, UV and optical, and then as we have large amounts of dust, we might not be able to see this UV and optical, but this radiation can actually heat the dust, and we might get the re-radiation by dust, and I will show some examples of that later in the talk. Okay, So now back to ARP299, which I use as an example throughout the talk. So as I mentioned, we did observe this substantial brightening of one of the nuclei, only visible in the infrared, not in the optical. So here I'm showing the light curves of this transient event in the near infrared. So that comes from the ground-based observations, and mid-infrared from the Spitzer Space Telescope. So this was very long-lasting event. So we did follow it over 10 years from the ground, and with Spitzer it was extremely energetic as well. So this to show the SCD of this nuclear region of ARP299. So by the way, these images are from Gemini North, taken with the adaptive optics correction. So here we see the infrared SCD before the outburst and then moving to after outburst. So we see basically this effect in the near and mid-infrared wavelengths. So these lines are showing radiative transfer modules for the dust heated by the starburst and AGN. So in ARP299, we have an important AGN as well, in addition to the starburst, like is the case in many other examples of luminous infrared galaxies. And then what we see here is this hot dust component, which we interpret as re-radiation by dust clouds in the polar regions of the dusty torus around the AGN. So the picture is something like this. So we have the supermassive black hole there at the center of the nucleus. We have a tidal disruption event occurring there, emitting potentially a lot of X-rays, UV, and the optical. We don't see any of this because we are viewing this supermassive black hole from almost edge-on direction in this case. So the line of sight is completely obscured. But then we are able to see actually the output as re-radiation by the dust clouds in the polar regions, which are not affected by such a lot of dust towards the observer. So what do we think this transient is? Well, we were lucky enough to get high-resolution radio VLBI observations where we actually see a strong radio jet, which we were also able to resolve, and we see the actual expansion of the radio jet here. And in the paper, we argue that this can't actually be related to the active galactic nucleus, that we are rather actually seeing a jet launched by the tidal disruption event in the galaxy. So we claim this is a dust-obscured tidal disruption event at the center of ARP299, not observable in the optical, only at the infrared wavelengths. So this is the picture. So we have the flare evaporating the dust up to a certain radius, and then the dust outside of this evaporation radius is absorbing and re-radiating some of the light. We get the delay between the optical and infrared because of the light travel time effect. So we talk about infrared echoes, and these are often seen for supernovae, and now also for tidal disruption events. So then we wanted to know how many of these might actually happen in local lurks and U-lurks. So we used the NEOWISE mission, which has a 6-month cadence. We observed all the lurks and U-lurks from the IRAS revised Bright Galaxy catalog of Sanders, and we selected transients similar to this one in ARP299 according to the luminosity. We detected a total of 5 smoothly evolving luminous transients. We did actually filter out a number of transients that did show stochastic variability, likely related to active galactic nucleus variability. So it was actually quite many, 5, it was actually quite many. So when you turn this into a rate, it's over an order of magnitude higher than the rate of optical TDEs or the rate of extreme variability of AGN. So in the paper we say that this is actually an indication of an enhanced rate of tidal disruption events in luminous and ultraluminous infrared galaxies. Very recently there has been a couple of more papers using WISE to observe similar transients in the nuclei of non-lurk and non-U-lurk galaxies over the whole sky, and these are happening apparently at similar rates to optical TDEs. So I think very interesting results. So then I finished the talk by showing a few slides what we might be able to do with Roman. So here we can't actually use the high latitude time domain survey because the field of view is not large enough. So we need actually a large field of view. So therefore we considered high latitude wide area survey, separating the observations into multiple epochs, maybe separated by 6 months or 12 months, because these are very slowly evolving transients. We did also consider including the K-band, which would provide very important color information for measuring dust temperatures, extinctions, and so on. Okay, so here I'm showing plots for a spectrum of a typical core collapse supernova a few months from the explosion after reddening the spectrum with different amounts of extinction. So we see that if there is 30 magnitudes of extinction, so extremely high extinction that we might get in lurks and U-lurks, we would still be able to detect such a supernova at 100 megaparsecs, so only very nearby galaxies. However, we should be sensitive to supernovae with up to 10 magnitudes of extinction to 250 megaparsecs. So it means that there is actually a fair number of supernovae to be observed if this was possible with Roman. So then turning into these luminous nuclear transients, so we use now a couple of previous examples here. So we have infrared SEDs, and again, we move these to different redshifts. So the question is that if we have an event similar to this ARP299 TDE candidate at a redshift of 0.5, we might actually still be able to see it in number of Roman filters. And then doing some quick calculations shows that we might actually be able to detect and characterize several hundreds of these kind of transients. So now moving from 5 transients from nearby to several hundreds of transients with Roman. So it's a big leap. Why this is interesting? Well, the current surveys are finding many TDE candidates. In the optical, there we see essentially no extinction. So there might be a dust-obscured TDE population out there, which the Roman could actually characterize. So then I finish with my summary slide. So basically, the ground-based and near-infrared and Spitzer and Weiss observations have revealed dust-obscured transients, supernovae TDE candidates within the nuclear regions of galaxies. And now if we were able to divide the high-latitude wide area survey into 2 or more epochs, we might be able to detect many more of these and characterize using the color information, possibly the light curve information as well. And this has important implications for using supernovae as probes of the cosmic star formation history, and then via characterization of the dust-obscured TDE population, possibly also for feeding of the supermassive black holes across the redshift and number of other topics in the galaxy evolution. So I finish here. Thank you very much.
Thank you, Seppo. So we've got time for one question. Let's go here.
So this is really cool. So Decker French has, in recent years, has found that there is a extremely high rate of TDEs, about 2 orders of magnitude higher than like normal galaxies in post-starburst galaxies in the local universe. And so this is, a really interesting connection to that population. Do you think that these infrared, dust-obscured TDEs in LERGs and ULERGs could bring those TDE rates up into that regime that folks are seeing for post-starburst galaxies as well?
Yeah, I think it's. Thank you. It's a very interesting question. So in number of LERGs and ULERGs, we can actually have even several supermassive black holes. We have these galaxies in the process of merging together. So I think we are disturbing the orbits of many stars. So I think that's opening up the possibility of actually increasing the TDE rate as well. Well, we only have these 5 events from nearby, so it's a small sample. So it's only an indication of an increased tidal disruption event rate. I think if we had the possibility to increase the sample, then we could do really interesting science with that. So thank you for the question.
Yeah, really neat. Thanks.
Thank you, Seppo. Let's thank Seppo again.